Welcome to the second module of this unit. In the last module, we saw that a CTL formula can be rewritten in terms of EX, EU and EG. We called it the existential normal form. In this module, we will look at algorithms for CTL formulae of the form EX5, E5 1 until phi 2 and EG5. So here is the CTL model checking problem. Given a transition system M and a CTL formula phi, find all states of M that satisfy the formula. This is the problem that we are interested in this unit. So in this module, we will look at the special case when phi is of the form EX phi 1, E of phi 1 until phi 2 or EG phi. Let's start with algorithms for EX phi. This is the given transition system and these are the labeling of the states with atomic propositions. We want to check if the formula EX P1 and P2 is true in this transition system. How would we do it? As a first step, find the states where this subformula P1 and P2 is true. Here it's not true, here it's not true, here it's not true. Here, since the labeling contains both P1 and P2, the subformula P1 and P2 is true in S5, P1 and P2 is true in S4. Once you do this, to check the states where EX P1 and P2 is true, look at the states which have a transition to a state labeled with P1 and P2. Okay? Look at S1. There exists an edge going to a state which satisfies P1 and P2. Similarly, look at S2. There exists an edge which goes into a state that satisfies P1 and P2. So, S2 satisfies this formula. Similarly, look at S4. There exists an edge. So this is an edge, right? There exists an edge back to S4 and S4 satisfies P1 and P2. Hence, S4 satisfies EX P1 and P2 as well. Okay, if you look at the computation tree starting from S4, there will exist a path which satisfies X of P1 and P2. And finally, this satisfies EX P1 and P2 as well because of this transition. Let me repeat this. The first step was to label the states where P1 and P2 is true. Then what you can do is consider each of these states. Look at S4 first. Look at all incoming transitions, as in the transitions that come into S4. Those states, so here there are two incoming transitions, one from S2 and one from S4. And the sources of these two incoming transitions will satisfy EX P1 and P2 because from these states there exists a transition to a state satisfying P1 and P2, which means from these states, if you look at the computation tree, there exists a path satisfying X of P1 and P2. We have looked at S4. Now look at S5. It is labeled by P1 and P2. Look at all incoming transitions. There are two incoming transitions, S1 and S4. S4 has already been labeled with EX P1 and P2. You need to label S1. Okay. Let us see another example. This is the transition system that is given to us, and we want to find the states of this transition system which satisfy the formula E x P1 and not P2. The first step, look at this subformula. It's made of P1 and not P2. Let's first mark the states that satisfy this subformula P1 and not P2. S4 is one state because it satisfies P1 and P2 is not there, so it satisfies P1 and not P2. In fact, S4 is the only state because S3 satisfies P2 and S2 does not satisfy P1. S1 does not satisfy P1. Okay, so S4 is the only state which will be labeled with P1 and not P2. The algorithm for Ex of P1 and not P2, what it will do, once it has labeled this, it will look at all incoming transitions to this state. There are 3 incoming transitions. All these states would be labeled with Ex P1 and not P2. So this state is labeled, this state is labeled, and this state is labeled. So this will be the set of states which satisfy Ex P1 and not P2. The initial state does not satisfy Ex P1 and not P2. Hence, the transition system as a whole does not satisfy Ex P1 and not P2, but there are these states in the transition system which satisfy Ex P1 and not P2. Let me summarize the algorithm for Ex5. First, we need to label states satisfying phi, and then once you do that, for every state satisfying phi, you look at its predecessor. In other words, a state S is labeled with Ex phi if there exists a successor labeled phi. This is the algorithm. It looks at every state of the transition system and marks phi first. Once it is done, it will look at predecessors of the states that have been marked with phi, and those predecessor states will satisfy Ex phi. So we are done with algorithm for Ex. Now let us see algorithm for E of phi1 until phi2, which is shortly written as EU. This is a transition system. We want to check which states in this transition system satisfy E of P1 until P2. First step, look at all states here which satisfy P2. S4 satisfies P2. So clearly S4 will satisfy E of P1 until P2. We assume that there are no terminal states, so there will exist a path from S4, and in that path the initial state itself satisfies P2, so S4 satisfies E of P1 until P2. Now what? Look at the incoming transitions to S4. S5, S3 and S4. In these incoming transitions, if the state satisfies P1, then label those states with E of P1 until P2 as well. S5 satisfies P1 and there exists a path which satisfies E of P1 until P2. So S5 satisfies E of P1 until P2 as well. If you look at this path, S satisfies P1 and S4 satisfies P2. Sorry, S5 satisfies P1 and S4 satisfies P2. Similarly, S3 satisfies P1 and S4 satisfies P2. So this path satisfies P1 until P2. So at S3 there exists a path satisfying P1 until P2. Fine. Now continue this process. Look at the predecessor of these newly labeled states. Look at S5. Look at the predecessor S2. S2 satisfies P1 and there exists a path to a state that satisfies E of P1 until P2, which means that this state will also satisfy E of P1 until P2. Correct? Because if there exists a path to a state which satisfies this, that means from this state there exists a path which satisfies P1 until P2. So from here also there will be a path which will satisfy E of P1 until P2. Okay, so this is a newly labeled state. Continue the process. Look at the predecessor of this state. There is one predecessor and it satisfies P1. So mark it with E of P1 until P2. Note that when we looked at the predecessor of S5, we also had S6. But since S6 does not satisfy P1, we will not mark it with E of P1 until P2. So these are the states of the transition system which satisfy E of P1 until P2. Let's look at another example. We want to check the formula E of not P1 until not P2 on this transition system. Let's mark the states of this transition system which satisfy not P1, not P2. This satisfies not P1, this satisfies not P1, this satisfies both not P1 and not P2, this satisfies not P1, S5 satisfies not P2 and S6 satisfies not P2. Now, what does the algorithm do? It first looks at all states that satisfy not P2. So this is the second formula here, no? Something until something. So it looks at all states that satisfy not P2 and labels them with E of not P1 until not P2. Because if you look at this state, there exists a path and already this state satisfies not P2. Correct? So this state will automatically satisfy E of not P1 until not P2. Same for S5, same for S3. Let us now look at the predecessors of these states. Look at S5. The predecessor of S6 is already marked. So let's look at S5. The predecessor of S5 is S4 and it satisfies not P1. So it has to be marked with E of not P1 until not P2. Similarly, the predecessor of S3 also satisfies not P1, so it should also be marked with E of not P1 until not P2. Now look at the newly labeled states, this one and this one. The predecessor of this satisfies not P1, so this has to be marked with E of not P1 until not P2. Now there are no more states left to be marked, so the algorithm will terminate. Let us now summarize the algorithm for E of phi1 until phi2. Assume that states with phi1 and states with phi2 are labeled. If any state is labeled with phi2, then we should label it with E of phi1 until phi2. That is the first step. Then we need to repeat this process. We need to label any state with E of phi1 until phi2 if it is labeled with phi1 and at least one successor is labeled with E of phi1 until phi2. We need to keep doing this until there is no change. Let's see. Suppose this state is marked with E of phi1 until phi2. Look at state S. It is marked with phi1. In that case, this should also be marked with E of phi1 until phi2. Okay, so this is the algorithm. You can check this with the previous examples. In the previous examples, we did E of not P1 until not P2. So we first marked the states with not P1 and not P2. Next, we looked at states where not P2 has been marked, and those states were labeled with E of not P1 until not P2. And then we did this step repeatedly until there was no change. You can have a look at it. We have seen the algorithms for EX and EU. Let us now look at an algorithm for EG. So here is a transition system. We want to check the formula EGP1. Here the algorithm would be a bit different from the last time. In the first step, label all the states with the formula EGP1. Now, you look at states which do not satisfy P1, S4, S5 do not satisfy P1. So first remove the labels from them. Now, look at the predecessor of S5, which is S6. Look at the paths out of S6, or rather the transitions out of S6. There is only one transition out of S6. And this transition leads to a state which does not satisfy EGP1. So we need to remove EGP1 from this state as well, because the only path out of this state does not satisfy GP1. So remove it from S6. Now look at the predecessors of S6, S3 and S7. Look at S3. Look at all transitions out of S3. There are two of them, one going to S4 and one going to S6. Both of them do not satisfy EGP1, as in we have removed the label from both of them. In that case, we need to remove it from here as well, because there does not exist a path satisfying GP1 from this state. Similarly, look at S7. The only transition out of it leads to a state which does not satisfy EGP1. So remove the label from S7 and S3 as well. Look at the predecessors of S7 now, S2 and S8. Look at S2. All transitions out of S2 go to a state where EGP1 is not present, so you should remove it from this state. Similarly for S8, the only transition out of it, so all transitions out of it lead to a state where EGP1 is not labeled, so we removed it from here. Finally, look at this state. All transitions out of it lead to a state where EGP1 is not marked, so EGP1 has to be removed here as well. In fact, no state in this transition system satisfies EGP1. You look at any state, finally it has to end up either in S5 or at S4. Any path from that state will have to end up in S4 or S5, and both S4 and S5 do not satisfy P1. No state in this transition system satisfies EGP1. Let's look at another example. This is a transition system and we want to check EGP1 on this transition system. First step, mark every state with EGP1. Second step, remove this label from states which do not satisfy P1, S4, S2. You remove the label from S4 and S2 because they do not satisfy P1. Now, look at the predecessors of these states. Let's start with S2. Its predecessors are S3 and S2 itself. We have already removed the label from S2. Now let us look at S3. Look at all transitions out of S3. There is only one transition and it goes to a state which is not labeled with EGP1. So the label at S3 should be removed. Now look at the predecessor of S4, say S5. S5, S6 and S1 are still marked with EGP1. Let's see what happens. Look at S5. There exists an edge which leads to a state satisfying EGP1. So we do not remove the label as of now. Look at S1. There exists a transition that goes to a state satisfying EGP1. So we do not remove the label from this state as of now. What about S6? There exists a transition leading to a state which satisfies EGP1. So we do not remove the label from this as well. In fact, these three states indeed satisfy EGP1. Since there is no change in the labels, the algorithm will stop. The algorithm starts like this. All states are marked with EGP1. Then states where P1 is not present, you remove EGP1. Then look at a state. If all edges out of it lead to a state where EGP1 is not marked, then remove the label. Now in the rest of the states, check this property. From every state, is there an edge which leads to a state marked with EGP1? In that case, do not modify this label. With this property, these three states, the labels will not be removed and the algorithm will stop. So if you look at this state, there exists a path that goes to S6, S5, S6, S5, S6, which satisfies GP1. Similarly, from S6, you can keep doing this again and again, and GP1 will be satisfied. Same for S5. Do S6, S5, S6, S5 and so on, and that path will satisfy GP1. Let us now summarize the algorithm for EG5. Step 1. Label all states in the transition system with EG5. Second step. If any state is not labeled with 5, then delete the label EG5. Then there is going to be a repeated step. Delete the label EG5 from a state if none of its successors is labeled with EG5. So let me illustrate it. First, all states are marked with EG5. Then, by doing this process, if you end up with this picture, that is, there exists a state from which none of its successors is labeled with EG5, then we need to remove the label from this state as well. We need to keep doing this process till it saturates, in the sense that we need to keep doing this till there is no change in the labeling of the transition system. Once you do this, the states which are labeled with EG5 are the ones from where there exists a path satisfying G5. So this is the algorithm for checking EG5 on a transition system. So in this module, we have seen three algorithms. Given a formula of this kind, we have seen how the algorithm labels the states that satisfy the corresponding formula. In the next module, we will look at a generic algorithm for any CTL formula.